to the end of the first week and half of the course, more or less. So between today and tomorrow, the plan is to finish the module 2. So we have a few more things to check about the physical layer aspects, okay, of 5G. And then next week there are 2 modules. One is about topology. So by topology we mean how you actually deploy the nodes in the network, and we'll see how this is going to look like in 5G, or at least what people are thinking of. And then the last unit, it's shortish, so we have 4 lectures, and this is about more, let's say, blue sky topics. So some things to do with stochastic geometry and complexity science. So these are kind of tools that are being considered. Stochastic geometry, definitely. Complexity science is more something we are developing in collaboration with IIT KGP. So it's not mainstream yet, but we have some results that show its usefulness. Okay, so that's the plan. So we have an exam today and an exam on the last day of the course, 17th, for those of you who stay the second week. We have another 3 tutorials, one tomorrow, one on Tuesday, one on Wednesday. Okay, and then there is this extra session by Professor Sanjay Kumar on Monday. It's very good, actually. I think it's one of the nicest people I met in my life, so it's definitely worth, for those of you who stay to attend and to meet him and to talk with him. He's a very kind person, very knowledgeable. Spent actually quite some time in the as far as I know, in the Air Force. So he was actually in charge of radars. He participated to the war of Kashmir, I think. So he's a very, very notable person. Okay, and then he went back to academia. He got actually a PhD in Denmark. He was in the same lab as me and Professor Suvra. He just started slightly after. So basically, I think he started around the time we were finishing. But I was also working with Sanjay. We published together, and he really took up a big challenge. He had family here, so he went to Aalborg in Denmark. Completely different weather, culture. You can imagine, right, with a family here. And he did very well, actually. Finished the PhD on time, good publications, got his PhD. Then he came back here. He went on to be actually a professor in BIT Ranchi, okay, in BIT Mesra, I think it's called, in Ranchi, yeah. One of the finest institutions in the country, as far as I know. Okay, so I mean, amazing person. Okay, and as Suvra said, it's not just that he had an interesting path of life and a good set of achievements in all the endeavors he undertook. But I think also he's a very complete person. So I find very, very fascinating that he can also he knows a lot about philosophy, yoga, so many more things than just the technical aspect, and that's a good thing. Yeah. Again, as a random tip, I think you become a better scientist if you are open-minded in general. You shouldn't just read technical manuals and papers. I understand, I mean, I do it myself. You have to read a lot of technical literature because it's what the job requires. You should spare some time to broaden up your thinking. Maybe reading, history of science, philosophy of science, or even beyond science. It helps you, I think, to become a better thinker. Okay, so I think that's a good thing. Try to travel if you can. Understand, there are sometimes family constraints, job constraints, but traveling is a very good tool to become a better person, in my opinion. Okay, and so these are just my suggestions. Okay, don't do things just for the sake of profit or CV. Learn a language just because you want to learn a language. Okay. Learn a new subject just because you want to learn a new subject without thinking too much how you're going to use it. Most likely you're going to use it. Okay, so I think if you learn something, like for example, there are some things that are really universal. So if you become better at math, it cannot be bad. If you improve your English or you learn another language, it cannot be bad. If you become a better programmer, I don't see any harm in it, right? So I think there is actually this concept of in few countries, not just in Ireland, it's called lifelong learning. That's what you're doing, by the way, right? I think you should keep on doing these courses, especially if I'm teaching them, because they're very good. Okay, no kidding. No, kidding. so that you should come back, you know, and attend young courses, other courses, and you know, and try to keep up, you know, the interest. Okay, and that's very important. I think you just become a better person by doing that. Okay, so today we are back to the waveform engineering. So we start to go into, so you already saw yesterday we kind of changed gear, right? So we started to go a bit more into math and technicalities. I'll try to keep it at a level that is still understandable by all the people in the room. And for those of you who are interested in going deeper, of course, you know, I'm happy to discuss offline. And I suggested reading material. Mostly I suggested papers I co-authored because I know them better, but I have other suggestions for extra reading if you want to go deeper. Of course, we are not the only ones working in these topics. There are many good works around. So I could actually, with the help of my team in Dublin, come up with a list of suggested readings that you should read if you want to go deeper in a topic. And yeah, so this course, I mean, is mostly meant to be a primer, an appetizer. Okay, so what the objective of this course is that you should hear the news about 5G. Okay, so I'm kind of breaking the news like I'm a journalist here, right? So I'm telling you what's going on. Okay, and I try to pick things I know better, but I also mention kind of other trends, though I don't cover them in this course. So hopefully I give you a comprehensive picture of what's going on. And the idea is just if you get like interested, if you get, you know, kind of curious about the topic, you know it exists, and then you go on, right? And I'm happy to facilitate, you know, you in the process if you want to know more, what the books are, what the good papers are, and but that's what it is. Okay, so you can't possibly cover 5G in depth in 20 hours. You understand that, right? So I mean, but hopefully at least some of the topics will be of interest to you, and then you can go deeper. But at least you know they exist after this course. That's what the course is about. So what is why is okay, so what is waveform? We are going back to that. So I'm just telling you why we are bothering about waveform design in 5G. Well, first of all, historically, that's what has kind of defined different generations. So there are other things, of course, but one thing that definitely defined former generations was the choice of the modulation scheme and how you do access with that, right? So we already saw that 1G and 2G were kind of a combination of TDMA and FDMA, sort of, right, in different you know, fashions. 3G was about CDMA, again in different, you know, fashions, but that was the king. 4G was about OFDMA, okay, and 5G, interestingly enough, I'm being very honest here, there was a lot of fuss because people thought that this kind of story would continue, that we would need a new waveform and, you know, to have a completely new PHY in all aspects. So people started to work extensively, including, you know, some people working with me, and they came up really with a lot of waveforms. So I'm going to give you a brief account in this course, but there are many. Okay, I would say in the order of easily 30, 40. Now, they have good points. Okay, so there are good technical reasons to do that. We are going to see some, and some new scenarios that are thought about in 5G need probably another waveform than OFDMA. On the other hand, the big problem with changing the waveform is that you have to change the mobile phones. You cannot operate the mobile phones if you just change the waveform, you know, to a new one. So anybody operating a network, we have some people here doing the real job of operating a network, they would know that you can't just, you know, come up with a new set of PHY techniques overnight and then hope the network will work. You would have to do radical changes throughout it, right? So that's why I talk with big companies, with small companies, you know, it's part of the job of being an academic in our field. They are all very, very, you know, resistant to this idea. And I talk to small ones, which is understandable. They maybe do not have the budget to do R&D, but I also talk with huge ones like Nokia. They are the same. They say, no, we are not going to do that, okay? We might do a bit of work and publish, but in the end, we don't believe that's the way to go, okay? They're much more positive, especially the ones that have the budget to do research, in changing possibly the infrastructure, or maybe distributing the functions, you know, this cloud process we discussed about, virtualization, because it kind of makes sense in terms of efficiency and cost. So they are kind of, at least they are looking into that. But when it comes to the devices, you are going to really mess up with the users, and you want to minimize that kind of story. Okay, so I'm warning you that the story has been very much academic. I think there has been very little adoption by the standard of what I'm going to tell about in the next 2 lectures. What they really did is to add some filtering, period. But they keep using OFDMA. And the variant of OFDMA in uplink, which is called single carrier FDMA, which is pretty much FDMA with an extra couple of FFT blocks, right? Yeah. But I mean, let's keeping that in mind, I'm going to tell you, part of the story that of the research behind it. You never know, maybe at some point we will have the right application, right, and this might come handy. And there are some applications that actually are, they make sense if thought under the under the viewpoint of a new waveform. So some scenarios, I doubt FDMA will work with those. Okay. So of course it's not just about the phi. Immediately when you change the modulation scheme, you are changing the way you do access, because access is just using the modulation in a way that you can serve more users. Like TDMA is like TDM, but you just use lots for different users. OFDM, when you start to allocate the subcarriers to different users, becomes OFDMA, and so on, right? You can go on with this story. So phi and Mach are definitely intertwined, and of course the rest too. Yeah, so basically you do have to design things keeping in mind the other layers as usual. You do have to keep in mind what the performance metrics you are after are. Okay, so if you have systems that do require high data rate, probably you are already bound to choose multi-carrier, or any form of multi-carrier. If you are maybe more about peak to average power ratio reduction, I think you should probably move towards single carrier. If you have a system with a lot of devices that try to transmit together, you have to make sure, I mean, ideally you would like them to be synchronized, but at some point it might be just too complicated. So things that require a very high level of synchronization in time and frequency, like OFDM, might not be the best idea. You probably have too much overhead in allowing them to be synchronized. If you have, say, a network with 1 million of nodes, okay, probably that's not the way to go. OFDM is very good when you have things that are kind of under control, not big numbers. You are targeting the maximum throughput achievable in the system, possibly. You want to schedule your users according to some central intelligence. That's what OFDM is really about at the system level, but there are some other situations where this is not the case. Okay, so what you have to optimize makes sense. And other things, for example, in some modulation techniques, you have to wait for many symbols to arrive, for blocks, before you process them, and that's against the latency, for example. Okay. Right. Other things have to do with, so there is always a duality between time and frequency. Whatever you do in time has repercussions in frequency and vice versa. Right. They're kind of the two facets of the same coin, basically. Right. And what happens, for example, if you what normally OFDM does, well, there are again other versions like in Wi-Fi and so on, but so far the story has been kind of that you just don't really do filtering. So you basically in time you just have a rectangular window which covers all of your symbols, and what happens then in frequency is that this turns into a sink, which is not a very nice function in terms of out of band emission, because it decays slowly. It goes like 1 over the frequency, so it takes some time before you know, it decays. Now, what's the problem? If you are alone in the universe, no big deal, but usually you are using the spectrum close to other systems, in frequency I mean close, and they are bothered by the fact that your out-of-band emission is slowly decaying. They would like you to be much more confined in space, right? So you can squeeze more systems. So all the story about cognitive radio, spectrum sharing, coexistence relies on the assumption that you can be very confined with your out-of-band emission. So again, OFDM, though there has been an immense amount of work about cognitive radio assuming OFDM, when you see even the pictures in these papers, you always see that they assume an ideal situation where you have really a rectangular kind of mask in frequency, which is not true in practice. Okay, so that gave rise, for example, to techniques like filter bank multi-carrier. Filter bank has been there way before OFDM, and it was rediscovered because of these new requirements. So you see, what I'm saying is, like, though it's true that possibly many of the things I'm going to tell about today won't make it to 5G, we shouldn't lose hope. At some point, you know, if an idea is good, it will find its way. An example from coding theory is LDPC codes. They were discovered by Gallagher in, I think, 1964 in his PhD thesis. Nobody could care less, okay? And then now, after probably, what, 50 years, they are among the two most successful codes in the modern communication systems, along with turbo codes. Yeah? Turbo codes were, that's another interesting story. Turbo codes were presented at ICC conference in 1993, if I'm not wrong, by a group, a French lab. And they, I mean, the legend goes that they kind of were laughed about, because they said, this is crap, this, you know, this is too simple, this, what are you that you come up with this? Because like the idea of turbo codes is kind of, you know, not so elegant even. They kind of, you know, concatenate some blocks, and, you know, they kind of, they even have things they show you, you don't even have these nice decaying curves. They decay very nicely up to some point, then you have an error floor. What is that? They say, come on, you should have curves that, you know, go to 0, right, at some point. But eventually, again, they don't laugh anymore, because now those guys became ultra famous, made probably a lot of money, and, you know, and this is one of the two dominant code choices, right? And you do have new things like polar codes and so on, but, you know, what really made it beyond convolutional codes, which were the former, let's say, dominant choice, are LDPC and turbo. And one was laughed about when introduced, and another one was even put there on the shelf and, you know, getting dust year in, year out. So what I'm saying is, like, if an idea is good, it will find its way through. By the way, Fourier transform was invented before probably electricity was there. You go back, right? Fourier is what? Early 1800s, something like that, right? So, yeah. So you never know. Okay, that's the point. Okay, so there are many things that bear some relation, you know, bear some you know, effect on the waveform choice. For example, the channel itself, right? So we know, for example, that the reason why you have cyclic prefix in OFDM is because you have to cope with the delay spread of the channel, right? Yeah, the requirements I discussed a bit. Yeah, for example, security too, right? I mean, or let's say, if you want to, you know, avoid interception, that's one of the reasons why CDMA is the way it is, right? So you see, in that case, what you want to get out of the waveform kind of, of course, influences the design, right? Yeah, and new applications like dynamic spectrum access, and definitely network aspects are important. So you do have things like etnets or small cells that kind of change the game, because now you are really packing many different transmitters in the same area. So I don't know if there is a study about that, but my impression is that if you go beyond some density, OFDMA might have problems, okay, because of this need of tight synchronization and also not so great performance in out-of-band emission. So the more you pack different transmitters in the same area, the more these two things play a role where OFDM is not doing so well. Yeah, synchronization and out-of-band emission. Of course, then people started to do work with OFDM because they don't want to disrupt things, so they started to add filtering, windowing. So that's the approach 5G is taking. They're basically, they don't want to change too much, so they are starting to play with filters. That's better than nothing still. Okay, so you have techniques like universally filter multi-carrier or filtered OFDM. They're kind of the same, where you basically change the story that you're just so what happens is, like, you know, so it depends also on how many subcarriers. So if you have a specific filter for a bunch of subcarriers, for a subset, for one. So depending on how granular you become with this filter, you actually get different performance. So originally, as we said, OFDM was about not filtering really, okay? And then there are techniques like FBMC, filter bank multicarrier, which are filtering each subcarrier individually. And then you have this thing in between, which is like filtering bunches of subcarrier, because the 5G is kind of is based on LTE advanced, and you do have these subcarrier blocks, right? 12, I think, per they call it resource block, right? So what they do, they apply a filter per resource block, I think. So that's the approach that it seems they're taking, okay? Which gives a better interference, let's say a better out-of-band situation, okay, than before. Power efficiency and power amplifier hardware in general are, you know, is an important consideration, and as I said, the choice behind the uplink modulation in 4G has been fully determined, or, you know, mostly determined by power efficiency. Okay, so the problem with OFDM is that you are summing a lot of sinusoids. Okay, and that leads to something like, if they are kind of aligned, you do have very high peaks. Okay, sorry, you're summing, yeah, sinusoids. Yeah, okay, so basically what happens is you start to have things like, you will have a sinusoid at the different frequencies. Some are, you have more lobes, but at some point you might have a situation where the sinusoids, because you're summing all of them when you create the signal, so you will sum the sinusoid at frequency 1, sinusoid at frequency 2, at frequency 3, so these peaks start to add up. But the average doesn't really change that much. It's the average concept itself, right? So you would have a peak to average power ratio, which is kind of high, which is bad for power amplifiers. Power amplifiers, at some point, they saturate, right? So they can't handle too high values of the signal they get in. So there are only two possibilities. You get better power amplifiers, okay, fine, which can handle higher ranges of the signal dynamics, or you play safe and you say, okay, I'm using a lower power, yes, because I'm basically not sure what will happen, but that's not the best thing to do, right? So they actually had to change the they had to change basically the modulation a bit in the uplink of LTE 4G, and they added like a DFT spread. So essentially they have an extra FFT block at the mobile phone, and an extra for uplink, and an extra IFFT block at the base station. Yes, and that's because of this reason. So you see, the requirements definitely have a big importance when you choose the modulation.
So sir, are we saying that OFDM is not safe for MIMO, whereas we can opt for FBMC when we are going for massive MIMO?
Yes, I think OFDM historically has a big advantage of interaction with multiple antenna techniques, and that's the same for massive MIMO. So, for example, so the main reason is like OFDM provides orthogonal subchannels, yeah, and a very simple way to do MIMO you could just apply your MIMO processing per subcarrier. You have to change nothing, literally. You copy and paste, okay? So there are some advantages in doing that. FBMC historically has had problems with MIMO, the simple MIMO. So filter bank apparently doesn't go well with that. But because of the degrees of freedom added by massive MIMO, we also have some work ourselves. They show that apparently it's fine, okay? But you have to kind of skip the MIMO steps, sort of. There are other new waveforms like GFDM. They are better off with MIMO itself, simple MIMO, yeah. So, but these are all considerations we have to do. And an important one, probably the most important one, comes last year, which is, oops, but you're not seeing the thing. Sorry. Should have told me. I thought, now I realize. Okay, you didn't miss much. This is still very intro. Okay, good. Yeah, just tell me, okay, if something is wrong. Because I was looking at my laptop, actually. Okay, sorry, my bad. Okay, now it makes sense. So the last one is actually the one that is probably most important, okay, because you see the kind of political business reason is what matters the most. So backward and forward compatibility, right? So this is kind of a big thing. So that's what I was saying before. The operators are very skeptical, the vendors too, in changing waveforms because they are implying a big change in the network, okay, in all devices basically. On the other hand, you could enable positive changes though, looking forward. So if you have techniques that are providing a better possibility for spectrum sharing, for coexistence, maybe that could give actually a good input to regulators to allow more of such things, more of spectrum sharing regimes, right? If you show them technically, look, I'm not going to disturb the current license holder, or anyway, we are two operators. Instead of selling the license to only one guy, you could sell it to both, and we are not going to interfere with each other because of a better modulation scheme. So you see, it is both ways, but again, not so easy to do, okay? And especially telecom operators, they have a kind of pragmatic mindset. They don't change what works, okay? So they have to have a huge business case, a huge reason to change the waveform. I don't think enhanced mobile broadband will probably require anything else than some tweaks to OFDM for a while. That's my impression. But other scenarios, so if this IoT, if this machine business really becomes a big one, it starts to be relevant, but you know, I still don't know if it's so widespread. I don't see it so widespread at the moment. It might be in 5 years or 10. Then I think no way you can do it with OFDMA. I mean, I'm kind of positive about that. You need something else. Okay, you need to change that. But you start from scratch in a sense. If you create a network to serve that, fine. Then you design it as it should be designed, right? Okay, so a bit of history. So you do, I already went through a bit. You know, you have TDMA in the beginning and CDMA, also some CDMA in 2G, but not only. Definitely wideband CDMA in 3G. 4G is basically FDMA and single carrier FDMA. You start to see they fiddled a bit with filters, raised root raised cosine, and then you have Gaussian filtering, you have square root raised cosine, and so on and so forth. So you have many variants of it. You don't have much of a filter in store in 4G. The most important thing for them was to make to provide orthogonality between the channels in the downlink, and to do that plus actually having some power efficiency in the uplink. Okay, but they didn't really bother to play with filters too much. Okay, now let's take a step back, because so far we talked, you know, about applications and so on, but what is a waveform actually? So it's essentially something that defines what you transmit, where and how, okay? So you can think of it as some kind of shape, some kind of pulse that carries information, and it has a well-defined shape in time and frequency, okay? That's really what a waveform is, okay? So you always have time and frequency, and you kind of shape the signal, and this signal carries information. Okay, so you can have things like on the left side, you see this blue and reddish plot where you are really actually you're not doing much in terms of localization. So you're kind of, you know, you have something more spread out. It's kind of like when you don't do any filtering, sort of. Okay, but then when you start to shape, you're kind of filtering your signal to be in some way. You can become much more localized in time and frequency. But it's really like, you know, a design space you can play with. Okay, and in general, you don't. You see, it's like it's a plane, so you can't change one dimension without changing the other. They are on the same plane, right? That's what I said about time and frequency being intertwined.
So these two things, one in frequency domain, the other one in time domain?
No, they are actually there. This is, I think, now this is very small. I'm trying to read it here. See if I get a better view. This is the y-axis. I think is not so visible. Is frequency and time. Yes, exactly. So yeah, but they are basically on the same plane, right? So you can't really you can't change independently one guy, because, you know, they're the same thing, right? So you have to draw the shape, keeping in mind both dimensions. And in general, if you narrow things, if you shrink things in time, you will broaden them in frequency, as you see here, right? Here we are becoming more localized on the left side in time, but that means we are spreading out in frequency. And if we want to squeeze the other one, we have to broaden the other dimension. Yeah. And that has big implications, because if you are worried about you know, being yeah, I think it depends on what you want to get from the waveform. So a big concern is out of band emission, which happens in frequency. So you have to play with time in order to avoid that. Okay. Good. So a bit of you know, of OFDM, though it's not 5G. Well, it's not the plain OFDM, but it's good to start from the 4G waveform. So you do have actually sinusoidal signal simply means a complex exponential. Okay, and each of these complex exponentials will be associated with frequency and carry a symbol that has been modulated before in a digital way. Let's say a QAM symbol. Okay. It has some properties that leads to orthogonality between the different subcarriers, and you do have actually a thing which is called cyclic prefix, where you basically, if you look at it in time, you are copying some symbols at the end of your signal. You copy them at the beginning. It's called cyclic prefix. It's cyclic and prefix. There are two reasons to do that. Now, the prefix itself, even without being cyclic, would be about basically coping with the dispersion of the channel to avoid intersymbol interference. Yeah, if you have multipath, you start to have different symbols messing up with each other. Yeah, you don't want that because it's interference. But you could do it without being cyclic. Why do they do this cyclic thing? Is because it has the property of making the convolution cyclic, which leads to very easy equalization. Okay, so basically you turn your convolution in time into a product in frequency essentially, and you can just equalize at any subcarrier by estimating the channel gain over frequency and divide it by that. So it's one division, one tap equalization for each channel, which is different, for example, what was done before in other generations. So there is a big advantage in terms of simplicity. That's why OFDM was so popular, not just in 4G, you have it pretty much everywhere, Wi-Fi, digital video broadcasting, and so on and so forth. Okay, there are really a lot of standards that adopted OFDM. It's because of data rate, yes, but it's because of orthogonality, but it's also because of this simplicity in equalization. Okay, so they do some smart tricks in the way they form the signal so that you get an easier job at the receiver. So no multi-tap equalization, no feedback-based equalization, a very simple receiver in the end. Okay. Good. The fact that you have access to individual subcarriers and they are orthogonal to each other gives a lot of freedom in terms of resource allocation. Okay, it becomes very easy to do to assign resources, to do power loading, right? Water filling. You could change you could apply coding, you know, for different sets of subcarriers. You could even have different MIMO techniques for different sets of subcarriers, right? It could be, for example, that in some subband you use Alamuti, in another subband you use multiplexing. Okay, it starts to be a bit complicated to design, but theoretically you can do it. Okay, so because you have access now to these things, which is something you would have to do playing with codes in CDMA. Okay, here you can do it in the frequency domain. And historically, it's very easy to do MIMO because you basically just apply MIMO per subcarrier. They are orthogonal, nothing to do with each other. I don't have to basically consider the frequency dimension when I do MIMO. It's like I'm doing it for a single carrier system. Okay, and then I repeat what I want to do per subcarrier. Any question or comment? Yeah?
What is water filling?
Water filling is actually, as the name says, it's kind of water filling, but with power. So what you do, you basically check the gains of the channel over different frequencies. Okay, in some frequencies it might be better, the channel, some others worse, and then you allocate power accordingly. So you actually, it's like you're pouring water. So you will have more power where the channel is weaker normally. You can also have the inverse water filling if your concern is not about making the situation fair, it's about maximizing throughput. Then it makes sense. If the channel is better, you do the reverse, right? You give more power, okay? Yeah, if the goal is to maximize the system throughput. Yes? What are the strengths of OFDM? Because, I mean, again, it was hugely successful. Probably, I would say, along with MIMO, the biggest success of physical layer research in the past 20 years. I think I'm not wrong in saying that. Okay, these two things have been really, you know, the most impactful. And I'm talking about academia, yes, but also the actual implementation and the way it's used in, you know, your phone will use OFDM, right? And many other things probably you use. And the Wi-Fi system you use will either use CDMA or OFDM. Yeah, so it's very, very successful. So as long as you make sure that your cyclic prefix is longer than the channel impulse response, so that the delay spread, you're good. You don't have any problem with equalization. Okay, and that also leads, because of this circular convolution property, you have a very simple equalizer. You know, literally, you just estimate the channel gain, you divide by that. End of the story. The cyclic prefix is adjustable depending on the environment. If an environment is more prone to time dispersion, because, for example, it's outdoor, you can have a longer cyclic prefix. Now, it's not so true that it's completely adjustable. In 4G, they have the provision for two cyclic prefix values. One is short, one is longer. Okay, and it's because the one is targeting more dispersive environments in time, one less. So dispersive, I mean how much time it will take before the former signal kind of the former symbol kind of fades away and doesn't disturb the transmission of the new symbol. Okay, when the multipath has done its job. That's what I mean by time dispersion. Okay, and you have to make sure you have some kind of guard band between the different symbols so that you don't experience inter-symbol interference. Yes. Velocity will have an impact on inter-carrier interference because it changes the Doppler, right? So that might move your carriers around. So that's why you have to be careful in frequency also. So there is inter-carrier interference in frequency because of the Doppler mainly, and in time you have inter-symbol interference because of the multipath of the environment. Okay. There are new waveforms that actually rely on processing blocks of information. It's normally fairly quick to do it with OFDM because you can process a symbol at a time. Now, not so true in the standard. They have to basically put together at least I think 20 such symbols, if I'm not wrong, and that turns out to be 1 millisecond of slot duration, but still it lends itself to fast processing. Okay, and you also have multi-carriers, so you're kind of parallelizing, right, the transmission, which is good. Why do they do, by the way, this multi-carrier? Basically what happens is, like, your channel is being selective over frequency. So that if you look at the channel response over frequency, it will change. Okay, and that what leads to complex processing at the transmitter and the receiver, or maybe you have to average out things, which is not really good in terms of representation of the environment. So what they did with OFDM, with multi-carrier in general, they basically divided this bandwidth into smaller chunks. They call it subcarriers, right? And if you make the subcarriers, let's say, spacing in frequency small enough, you are going to see something like a constant, right? No matter what is the actual channel response in frequency, if you make your subcarrier spacing small enough, you're going to see something constant, which is good in the sense that, again, you can have one-tap equalization and you don't have to average things. You can do the best decision. You can take the best decision in terms of power, modulation, because you know exactly what the channel is. But if you start to have to average out, then you're taking a suboptimal decision, plus you have a complex equalization. Yes? So that's kind of the reason why you do multi-carrier. Okay. Yeah, and it can also actually be adapted to become single carrier. If you have these extra DFT and IDFTs spread blocks, what they do in uplink of 4G, it turns out to be, because it's like saying I do IFFT and FFT, they are the inverse of each other, so it basically end up with one carrier again, and that's how they do uplink in 4G. So it's a very flexible technique. Okay. But there are weaknesses. That's why I'm talking about new waveforms in a sec. And basically, the weaknesses have to do with the synchronization. Okay, you do need a lot of synchronization going on. You do need synchronization in time and frequency. Okay, and that becomes more and more complicated if you increase the number of transmitters in a certain area. If you increase mobility, right? So these things are not so easy to cope with. Carrier frequency offset could be a problem too. So you could have, for example, situations where you have a distributed system like comp, where the local oscillators are not necessarily experiencing the same carrier frequency offset. The carrier frequency offset would be the same if they are on the same if they are in the same physical space, right? Because the circuitry is common. But if you start to have separated things, you start to have changes in that, so it's not so trivial to cope with that. If you have mobility, you have a carrier that starts to move around because of Doppler. And again, OFDM is good if things are kind of, not so complicated in terms of these impairments. If not, it starts to be a problem. Poor spectrum localization, I already discussed that, right? So definitely it wouldn't go down very well if you start to have a very dynamic spectrum sharing with systems really being very close in frequency and in space. Then OFDM would start to have problems, okay? Because you have a high out of band, which is interference essentially coming from another system operation. You do have the need of cyclic prefix, which is not useful data. It's just something you add to avoid issues with intersymbol interference, but that's lost, right? It's a loss in spectral efficiency. So you can't get the full throughput possible if you use OFDM, because part of your band is going to be used for these guard times. Cyclic prefix is guard time, basically. You might also need frequency guard bands, okay? So guard time is because of the intersymbol interference. Guard frequency, guard band, is because of the out of band emission. Okay, so these things are again basically it's a poor usage of your spectrum. It's not going to help with spectral efficiency. So what people did is to try to apply some filtering, right? And they did window FDM, universal filter, multi-carrier. They started to cancel subcarriers, so put in nulls basically, simply. Okay, that's the simplest thing you can do instead of doing very complicated filtering. If you are prone to create trouble to the adjacent band, you just put zeros there, and that's it. Okay, of course, again, not so ideal. There is a new technique which is called GFDM. I'm going to talk about it in a sec. Some people are even publishing papers on CP-less OFDM. So they get rid of cyclic prefix. One person working in in my university is working on that. I don't know exactly what they do, but they do have probably they apply something like time reversal technique, something like that. But they kind of show that you can actually do OFDM without necessarily needing a cyclic prefix. Okay, so research is evolving to cope with the problems of OFDM. As I said, the two vastly most successful techniques so far in physical layer have been OFDM and MIMO. So the category of techniques is waveforms and multi-antenna, and they are families, right? So there are many things inside it. So waveforms, you could classify them as orthogonal or non-orthogonal. So OFDM, which we discussed so far, is basically orthogonal, and there are other techniques like filter bank or single carrier FDMA in LTE uplink are all orthogonal. Then you have new techniques like the filtered multi-carrier, the generalized frequency division multiplexing that give up orthogonality. We are going back about why that's a good idea. And MIMO, you could have it as we saw so far with co-located and distributed antennas, right? So that we already saw. Any question? So visually, probably it's easier to see what I mean by these different techniques. So FDM, essentially, you see you have a time dimension, x-axis, and the frequency dimension, y-axis, okay? So FDM, you see, creates subchannels in frequency, and then it copies part of the symbol in time at the beginning, cyclic prefix, yeah? Single carrier FDM is sort of what they do in uplink of LTE. So it's like FDM, but they kind of reverse the picture because they add this extra FFT at the beginning and extra IFFT at the end of the transceiver chain, and essentially they kind of overlap channels. So you don't have, if you look at it as a system, you have a single carrier system, so you do not have multiple channels in frequency anymore. But if you are after the first FFT block, you have access to multi-carrier. That's why I say it's a kind of fake single carrier. But if you look at it at the system level, like from the transceiver viewpoint, it is a single carrier. That's why this representation is correct. So, but in fact, it's a kind of hybrid between single carrier and multi-carrier. That's the uplink of LTE. GFDM is sort of like FDM with two differences. They process actually blocks of symbols. So FDM, you can do the processing per symbol in time. Here they kind of collect many different symbols and they just use one cyclic prefix for all of them. So it's like OFDM, kind of, but OFDM would have a cyclic prefix for every time symbol, right? But basically what they do in GFDM, they add other time symbols, so many more samples, and they still use one cyclic prefix. Okay, they have some reasons to do that, and they give up orthogonality. So they do not necessarily want subchannels to be orthogonal. Why would that even make sense? Okay, again, if you think of situations where orthogonality might be difficult to achieve, why don't you give it up in the first place, designing a waveform with that in mind? That's the idea behind these non-orthogonal waveforms. Okay, they are meant to work for situations where synchronization is difficult to achieve. Okay, so they did the design in the first place, giving up this assumption that different channels have to be orthogonal. Okay. This is another visualization of the difference between these two waveforms. So you see what I'm saying is basically in OFDM you would have essentially basically you would have n subcarriers, capital N, right? So you would have basically a modulated symbol like QAM for each subcarrier. You would have n of them, d0 of 0, d1 of 0, dn minus 1 of 0 at time 0. You would have n samples. You take the last number, maybe a small number less than n, you attach it at the beginning, cyclic prefix, and then you keep doing that for every time symbol, for every symbol time. So you have this number within the brackets. It's the current index in time, yes, 1 up to whatever. If you take the same structure in GFDM, it would look like basically removing the intermediate cyclic prefixes. You would just have 1 at the beginning, okay? And one immediate consequence of this, I mean, there are 2 consequences of this approach. Again, they have to do this to achieve what they want, which is a more robust system against lack of synchronization, essentially. They gain spectral efficiency because given the same amount of samples, they use less of them for cyclic prefix, which is lost, right? It's overhead. The disadvantage of this, though, is that you have to wait for m time symbols before processing, right? In OFDM, you can do it every time. Here, you have to wait until you get all the bets. They even claim this is good for latency. I don't see how. Honestly, I think this is not good for latency, okay? But again, it depends on what you want. Okay, not too bad the time. So, yeah, the full name of GFDM is kind of recent technique. It's probably one of the newest modulation techniques from the end of the last decade. They use a transform which is not the usual Fourier transform. It's called Gabor transform. You don't use rectangular windows in time, so they change the thing that you don't filter. They do filter, okay, and that has repercussions. That's another thing they change. So in OFDM, you basically have this rectangular window in time, which leads to sync in frequency, which is bad because it decays slowly. If you do something smoother, let's say you do raised cosine, the smoothness you have in time implies that you have a faster decay in frequency, right? You get something that goes down maybe as 1 over f squared, 1 over f cubed, instead of 1 over f, which is good again for cognitive radio and all of these things, right? Now, non-orthogonality, though, has its own problems. You start to interfere between subcarriers. You start to have intercarrier interference, not because of Doppler, just because of the design you make, yeah? So they do have to do some extra successive interference cancellation. So they have to complicate things a bit at the receiver to cope with these problems. There's been like a big amount of research in the European Union about this. There are big projects like this 5G Now and others, and they showed, for example, how you can use this kind of new waveform for cognitive radio, for machine type communication, where you have you can actually have a low synchronization cost, and for things I'm not so sure about that, but they also claim that you have low latency applications. Probably you can play with blocks to be small. So this M I showed here could be probably small, I guess, but still I don't think this is better than OFDM for latency. Okay, but they basically, I think it's fair to say that for things like spectrum sharing and things like densely deployed environments like dense cells, really ultra dense cells deployment, or machine type communication, IoT, where you have a lot of sensors, this might be a better technique than OFDM. You have different ways to do the filtering. You can do many things, okay? There are papers that talk about that. You can do windowing, which is kind of, again, making the signal smoother, overlapping some portions of the signal. So there are some techniques. We have some papers on these things if you're interested. The drawbacks, as we said, lack of orthogonality. You might actually still need, well, they have less cyclic prefix, but you might end up needing a cyclic suffix maybe. Open issues, time varying channels are still nasty. So you might have to design the filter keeping, for those scenarios specifically. And you do have successive interference cancellation, stuff like that at the receiver, which is complex. The good thing about OFDM is that you have this one-tap equalization, simple equalization. This is changing. So you see, you never gain on all fronts, right? If you tweak something to benefit, in some way you are going to lose in some other way, clearly, right? So if you say I'm relaxing orthogonality, and that is good because it gives me it's cutting me a slack for synchronization, and I can do better in that sense, and I can coexist better because of the filter design I'm doing. On the other hand, you're making things more complex. So we are saying this is good for IoT, yes, but IoT has to be simple. So probably it's only good if IoT is uplink, right? Because you could have like the gateway or the proxy more complex, which is, by the way, what it is. Probably it's not so bad as a deal. So if you are just complicating things at the receiver in uplink, it's probably okay in IoT, because most of the traffic is uplink anyway, yeah? Probably less true if you are applying this to a cellular system. But for cellular systems as it is, I think OFDM does a great job. I think all of this waveform, I heard at some point people saying these new waveforms could substitute OFDM. I think that's really not correct. I think I don't see big changes in the modulation front from 4G to 5G for the mobile broadband application for smartphones. If ever these new markets about critical IoT, massive IoT will pop up, then you probably might see something like that. Okay, but even there, honestly, there is always a divide between academia and industry. So what they are doing with my impression, a lot of the work that is happening with machine-to-machine communication is using 2G. Okay, forget about 5G. Right? So GSM, great. Okay, so we are happy with that. So again, I think you have to keep in mind the ethos, the rationale behind an organization. I think a research lab in a university is it's like a wildfire, right? Okay, let's do this, let's do that, great, let's change everything, and who cares, new paper. But of course, it's very different if you are in the industry, or if you are on the end user side. And that's what it is. I think as long as there is some cross contamination and discussion is good. I think it's fine. Okay, I'm not against this. Maybe sometimes it's too much. Okay, people they start to say, okay, what if we put 1,000 antennas in a mobile phone? Okay, what do we do with that? But of course, you might think about something, and then you have quantum. I mean, there are some people in my lab I think are mentally insane, and they go after everything literally. And I think it's good. Okay, for a science lab is good. But then, of course, there has to be somebody like me trying to negotiate, and mediate the crazy ideas. I think the good thing, if you have a lot of good and crazy ideas, some of them will work. We are playing with diversity. I don't believe all of them will work, but the example of these LDPC codes is a good one. Okay, something that kind of looked very theoretical and useless, it turned out to be very useful. So, and again, the Fourier transform was invented by Joseph Fourier when telecom was not even close to come, right? So keep that in mind. I'll stop here. We start again. So we have a Q&A session at 10:30, if I'm not wrong. Yes? Yeah? And then I'll start the new lecture at 11:30. So if you're interested in Q&A, you can come here in half an hour, more or less. Okay? Thanks. Yes? Yeah, sorry. Wait a sec.
Sir, you have to just remove your laptop.
Yes, sit down, no problem.
Part of the course on new waveforms. So I just give a bit more of details now. I do have papers that are more explanatory, and also there is a PhD thesis from our lab. I think does a very good job about explaining these novel waveforms and how you can, for example, also do some modifications to OFDM to make it suit better the new requirements of 5G. Essentially, you see you have synthesis and then analysis filter bank. You do upsampling. you exploit the properties of circular convolution, and then you still have the CP, the cyclic prefix addition and removal, like in OFDM. Okay. Essentially, you have M. So you're basically doing FFT for each block as many times as you have time symbols. Right? We saw that GFDM is about grouping together time symbols, and then you use one cyclic prefix. But there are similarities, of course, with OFDM. It's still an FFT based technique. So what you could do is to model your signal. Actually, you see you have to stack together different vectors because you have different time symbols. So in this case, for example, each of these vector would actually be like the time dimensions. You would have m symbols, and then you have n of these vectors, which is the frequency dimension. So for each OFDM symbol, you would have n samples, where n is the number of subcarriers. In GFDM, you would have m times n, where m is the number of time symbols per block, and n is the number of subcarriers. So you just increase the number of samples you process at once, which makes it like more block-like processing. Okay, I'm not going into the details because it's probably not so relevant for this course. But again, I have the paper cited, so you can check better what this matrix has inside exactly. But you see, it's a very simple model. So we are still using something that is fairly intuitive at the transmitter, at least. Okay, and then we proposed actually linear techniques at the receiver, trying to reduce the complexity. Okay, and again, there is the math in a journal we published in 2016. What I can tell you again, for what it matters, because it's just one sample is my story. This paper actually is one of the best cited papers in my collection. Okay, so again, one sample, maybe other people will tell you a different story. Just to tell you that there is, at least from the academic world, quite a bit of interest in these new waveforms. Okay, I think the most cited papers I have are about well, massive MIMO, new waveforms, and still there is quite a bit of interest on flexible spectrum access, spectrum sharing. These three things are very popular, apparently, just based on the citations I see, you know, about my works. That's what I can tell you at this. Okay. So the model is general, so you can just do some tweaks and change a match filter into zero forcing into an MMSC. There are some things we do with processing matrices we use that are essentially they are in block circulant matrices. So they are very regular matrices eventually. It's because of all of these circular convolution and FFT properties, you end up with something very regular, which is good for signal processing, because you don't have to essentially, if you want, account for all the matrix. You just need to account for a block of it, and then the rest is kind of a repetition. So it's very efficient also for storage, for processing, stuff like that, because there is a big regularity in the modulation matrix. Okay, that has good repercussions in the computational complexity. Even within the block matrices, what we found is that they are circular themselves. So you actually just need to know the first column of a submatrix of the whole matrix. So it seems that this regularity, so we found it in OFDM, in GFDM. It seems a lot of these waveforms that are based on FFT are very, very regular. So if you have a modulation matrix means the modulation you multiply the transmit vector by, okay? And then of course the game is to, at the receiver, to try to invert that matrix to do the demodulation. So if the matrix is very regular, of course it's much better for the signal processing, right? Because for storage and even the way you represent it is very nice, okay, and very easy to manipulate. So we found actually can reduce the complexity quite a bit, also with OFDM. Okay, good. So you see, that's what I'm saying. So everything is based on this very regular matrix A, and then you can do your, you know, MF, ZF, MMSC, and you know, they are all different techniques, but they are all very they're all simple. Okay, they're all linear. That's a good thing. There is a thread of work on GFDM that uses successive interference cancellation. So they assume nonlinear, a nonlinear technique at the receiver. That's another class of receiver. They will do better, of course, than linear receivers. We are not doing that. We are just saying, okay, assuming that you are sticking with linear receiver, we decrease the complexity. But you know, you can't compare pears and apples. So if you compare with something more powerful, of course, you'll get a better performance, but you'll also pay a price in complexity, right? We are on the cheap side, and we try to make it cheaper, okay, so to speak. Of course, with the limitations due to the fact that you are using a linear receiver. This linear versus nonlinear story comes back when we combine the waveforms with MIMO, okay, with massive MIMO. Okay, so another example of new waveforms, you can use this filter bank multi-carrier. It has an interesting story because it's been there for a while. Quite a while, actually. We are talking probably something in the order of 50 years or more. It was again rediscovered recently in few fields, not just cellular communication. They also use it in underwater communication. It seems to, yeah, it seems to be good for that. I'm not an expert in underwater communication, but just to give you an idea that wireless is way more than radio. In that case, they use acoustic waves, right? Yeah, because you can't really do much with radio waves underwater, right? And they do have a much lower carrier, a much smaller bandwidth. But what they call so the broadband definition is not universal. It is essentially the relation between the system bandwidth and the carrier, right? So if this relation doesn't depend on the numbers. So you could have a broadband system using a much lower carrier and a much smaller bandwidth, or vice versa if you go to very high frequencies, right? Millimeter wave, right? So keep in mind this. And so the point is, many techniques that we designed to be broadband, they can be used for other broadband systems. And that's why, for example, filter bank can be applied to both domains, yes? There is a postdoc working with me. She's doing work on channel modeling for underwater. So there are many challenges that are way beyond what we think is our domain, okay? So you do have open problems in space networks, okay? You have open problems in underwater networks. So, you know, I recently visited another university, and they do underwater experimentation. They have literally bathtubs. Right, that's what they have to do, right? It's not their USRP like kind of thing is underwater, and they have it's not USRP, but you know, they do have this kind of test beds, right? And of course, it's very relevant for submarine communication, oceanography, right? So there is actually a big community even within the IEEE, like this international organization, right, of electrical and electronic engineers that focuses on underwater. So this is still pretty relevant actually nowadays.
Do you have any reference for this underwater communication?
I can ask to the person that is leading that work in Dublin. If you just send me an email, I think there are projects also both in US and in Europe. Definitely this popular. I mean, it's not mainstream, but it's relevant. Okay, so there are actually it's an interesting thing. And other things are about space networks. Okay, so you could think of it's not just satellite, it's beyond that. You could start to think about space exploration, and there you have to play with delay tolerant networks, right? Because the distances are very, very large. And again, you know, these things are a minority. Is not, you can't say this is mainstream, but I'm just trying to say that the 5G story is just a part of the modern wireless engineering story. It's way more than that. And we are not bound also to necessarily use radio, right? You do have optical fiber, you do have Li-Fi, you do have people working on quantum, which is very fascinating as a field, very much not technology ready, but there is a lot of open questions. And you see the trick with quantum, for example, is that you have this quantum entanglement. I mean, I tell you the little bit I know, which is not bound by physical distance. So it's sort of the, if two, let's say, particles are coupled, they're coupled no matter how far they are, and if one changes state, the other will do, regardless of the distance. So in a sense, you could cheat. Speed
China has already done quite a lot on quantum.
Quantum, I think, has been there for things like the music going on somewhere. No. So basically, quantum has been there, I think, mostly for cryptography,
Yes.
key generation and distribution. I don't think there has been so much work communication and networking wise. Yes, it's coming up though. It's another trend that I think is good to keep an eye on. The advantage about that, if you could possibly use it, is twofold. I think first of all you have something that is not so bound by speed of light. Again, I'm not a theoretical physicist, but this entanglement is something that could help you with long distances. Another thing is the capability to compute beyond the bit. So what they have, for example, you might have heard about people doing work on quantum computing. This is something also that is coming up. And you're not bound to use zeros and ones. You're actually, you could use all the values in between, right? So you could possibly exponentially increase the computing capability. Okay, so it's just keep an eye open. There are many things coming up beyond, let's say, 5G and so on. Okay, going back to 5G, the windowed OFDM is about actually smooth transitions at the symbol edges. So you're kind of having this gracefully decaying signal in time. So the problem is, when you have this kind of hard edged filter, like a rectangle, there are two problems with that. So one is the counterpart in frequency we said, right? It's a thing which is not really a very nice function in terms of out of band emission. Another problem is that these are not really easy to engineer. So whenever you have a picture which shows you very ideal things, beware, okay? Because these things are normally, this is a more natural, signal in a sense, okay? And it has some repercussions in terms of frequency response. So just to give you an idea how things work, so this is essentially showing what happens to the frequency response for different multi-carrier techniques. So you have OFDM, you have filter bank multi-carrier, and they have a windowed OFDM where you have this smooth filter right in time. 25% here means that they are extending the symbol period by 25%. So this 25% is the time it takes to add this. So it's this additional roll-off period. And you're doing way better than OFDM. Okay, of course, FBM still filter bank can do much better. Now, filter bank, as the name says, it kind of has a filter embedded from the beginning of the design. As Suvra said, some things are just meant to be for some applications. So they design filter bank having the filtering concept in mind. So it's not surprising that it does a better job in filtering, right? Window OFDM is just a patch we put on OFDM to make it, better in terms of out of band emission. But filter bank was designed for that. Now it has other problems. For example, integration with MIMO is not so easy. But it's probably that waveform, in our experience, doing the best job. So if you want to make sure the leakage is minimal, filter bank is probably the way to go. Not OFDM, definitely. Even if you have filtered OFDM, it's not going to be as good as filter bank.
So how does FBMC in terms of mobility?
Mobility. Yes, good question. Now, filter bank would mean, I don't know if there are really studies on that. I know some people, well, if you talk about highly mobile systems, there is a colleague of mine who's been doing work on another waveform. It's called OSTF, orthogonal space-time frequency modulation, possibly. I'll have to find out. Okay, if you again send me an email as a reminder, I'll find out. But he has a recent letter. I think I'm going to find it. It's a wireless communication letter. And that's been designed with very high mobility in mind. Okay, so something like high-speed trains. They do some trick where they change the. So the problem with high mobility is that you have a very dispersive channel. They kind of do some trick with something called, is it Heisenberg transform, and they turn it into something static. I don't know that is kind of magic, but you know they do some stuff. Let's see if I find it. TSF letter. I think I'm going to find it. Okay, this is the guy. Now I'll just have to check the publication, then we open it. It must be not a two-sided one because it's recent. Orthogonal. We'll find it. TSF, SFT, TSF, SFT, letter. We'll find it. Give me a sec. Now the guy doesn't seem to update his own website. Okay, I'll try another time, and then if not, I'll find out offline. Could be that it's still not, maybe it's accepted but not published. Anyway, you know, so I'll find out. But yeah, they do have actually some design of waveforms explicitly targeting high mobility. I think filter bank, I think it works fine when you have very dense environments with a lot of communicating devices. I'm not necessarily sure how it fares with mobility. It's probably the best advantage is, I think it works better than OFDM in cognitive radio, right? Because it kind of, it's more confined. If you look at this picture, you see that it's kind of, so maybe it's easier if I go here. So if you have like an OFDM cognitive radio, let's say your limit of acceptable interference is minus 30 dB, maybe. So you would have to basically go this far in frequency before you can put another system operating. But with FBMC, so you see this is all spectrum you gain, correct? So I mean this is a fact, right? So I think of course there is standards and there are FBMC has its own problems. Main one is the one of the main ones is the interaction with MIMO. OFDM is doing a better job, you know. But if you just look at a single antenna or maybe massive MIMO, you just skip the MIMO part, then FBMC does a very good job in terms of spectral confinement. Another version which is similar to windowed, like to filtered OFDM, just a bit different. So they do filter groups of subcarriers instead of, so what OFDM does, it basically uses one kind of filter, a rectangular window for all the subcarriers in the system. Bandwidth, okay. For filter bank multicarrier has the possibility to filter per subcarrier, to become very granular in the way you do filtering. Universal filtered multicarrier is in between. So you actually filter blocks of subcarrier. One of the reasons they thought about it is LTE, because LTE is based on resource blocks. So the unit of allocation is not the single subcarrier, it's 12, right? And then you have, how many symbols is that? 7, possibly? Don't remember right now. So you have some number of symbols in time and 12 subcarriers in frequency. So it makes sense because you can't allocate less than that. You can only allocate multiples of 12 subcarriers because of the way the standard is implemented. So if you want to actually filter things precisely, the best you can do is 12 by 12. And this technique is good for that because it has the possibility to filter groups of subcarriers, okay? Good. Yeah, so there are many different flavors of filter bank multicarrier. Going back to this, but there are really many, okay? People are really looking into that. So you have things like the filter multitone FMT, which has been there for a while. I'll show you a bit more about different filter bank specific techniques in a second. You do have other things that rely on quadrature amplitude modulation. You do have pulse amplitude modulation. So you know they all have pros and cons. These are minor variations on the theme, though. I mean the main concept is still filter bank. So what are the objectives? I mean, in the first place, why should you change OFDM? Well, one reason we already said, spectral separation is you can do a better job with filter bank because you have lower level of adjacent channel leak ratio. Okay, you basically spill less energy, less power into the adjacent parts of the spectrum, right? So if you can actually be more efficient, you could pack more systems. You can pack more operation, more like transmissions, right? Which is probably good. And the fact that you are actually this filtering is done in a way that you kind of give up orthogonality between subcarriers, which again is probably fine if you are not really capable of achieving tight synchronization in the first place. OFDM has a problem in assuming that everything is very synchronized, because if you start to have scenarios where you have a lot of transmitters in the same space, it's difficult to achieve that. So if you give that up in the first place, it's not a problem. You are declaring that's not what you are after. Okay. You don't use, actually, an important thing in filter bank, you don't need the cyclic prefix. So you don't need these guard times that you have in the 4G modulation technique, which is OFDM. It can work without cyclic prefix somehow. Okay. That's why people have started to look into cyclic prefix less OFDM to fight back. Okay, but natively, FBMC doesn't need cyclic prefix. Yes, which one? It's adjacent channel leak ratio. It's like out of band emission, basically. So it's like something like that. So the main lobe is actually what you are transmitting, and the rest is just spurious, right? Emissions. You're just disturbing others with these secondary lobes. That's what it is. Okay. Any question or comment?
Yeah, I have a question.
Yes, please.
So actually, is it possible to interface FBMC with SSK phase shift key?
Phase shift key. I'm aware of works actually that use these modulations possibly. I would have to look it up. There would be a reason though to do that. I mean, they are, what I understand, they are still trying to do things that are kind of simple in terms of modulation. So, you know, even binary, that's probably okay sometimes. So it seems to me they are building up from very simple modulations. You know, they're starting from those. PSK, it depends on what. So probably that's okay. That's good in the sense of PAPR like stuff maybe, and possibly there could be a reason. Again, I could speak with the researcher leading this area in my college, and if you send me an email, I could ask him to give you some, you know, he definitely knows if there is work going on there. I didn't hear about it. That doesn't mean it's not right there. I think the main ones are pulse amplitude modulation and quadrature amplitude modulation. That's what seems to me the dominant choices. Yeah. Any other question? Just checking time. So when do we have to go for the picture? 12:30. Okay. Do you mind? Any more question? No? Yeah. Okay. So that's just to show, okay, what different possibilities for the shaping filters are. Okay. So you have like the staggered multitone SMT. You have the cosine modulated multitone CMT, and you have the filtered multitone FMT. Okay. So FMT doesn't need to overlap between subcarriers, so we are in the frequency domain. CMT and SMT do. Okay. So and they do it on purpose. They actually want to save bandwidth. Okay. But they have to give up orthogonality. Now that's why one option is to actually toggle phase between adjacent subcarriers so they don't interfere much with each other. So it could be, for example, I'm going back to that, but you could, for example, have things like phase of 0 or pi over 2, which are orthogonal, and you could allocate adjacent subcarriers with different phases, the symbols. Okay, that's an option. Another way could be to consider only the real part of the signal, because you are kind of confining interference and noise to be on the imaginary part. So they are doing some tricks to alleviate the problem of having overlapping subcarriers. Okay, so that's not good. I mean, it's okay that we are relaxed in terms of synchronization, but still it's worse than orthogonality, right? So they are still trying to cope with the performance loss due to the overlap. So they are doing some upgrades. So that's what I was saying. Okay, so you basically have, let's say, the time frequency lattice we saw in the beginning of today, and you could, for example, alternate the carrier phase to be 0 or pi over 2, and that's limiting the intercarrier interference. Okay. So one way to do CMT modulation actually is so cosine modulated modulation is to basically use VSB, vestigial sideband modulation. Okay, you might have heard of it. And what you do essentially, so you see the top figure, you have actually the spectra of the baseband data streams, okay, in black. So this is the broader trapezoid, and then you have the colored narrower trapezoid. This is actually the vestigial sideband portion, the VSB portion of it. And then you basically modulate these baseband signals and to the frequencies of 0 up to Fn minus 1. Okay, that's one way to do it. It's not the only way to do it. Okay, so actually all of these techniques are very related. So for example, SMT and CMT are very much the same thing, just with some phase difference, I think. So this, yeah. So they're kind of all related, okay. And then also like the FBMC, OQUAM, QUAM, PAM, they are all doing some tweaks, okay. They're all in the family of FBMC, but you know, they have some kind of minor differences and disadvantages and advantages, but you know, they're kind of related. Especially SMT and CMT are sort of the same thing. So that's to give you like some schematics how the modulation is done. Okay, so you see we just take the real part, because actually in the system model we show that the interference and noise are confined to the imaginary part of the signal, so you just get rid of that. And then of course when you demodulate, you have to bring back your vestigial sideband modulated signals to the baseband. Okay. Now, so far in the phi part of this course, we discussed about new waveforms, we discussed about massive MIMO. Largely speaking, they are after the same thing. They are about serving a large number of users, right? Anybody guessing why this is true? So don't just trust me on that. So why, anybody that can tell me why they are both about serving many users, more than we can do nowadays at least?
Density area, large number of people.
Yeah, so FBMC is good for that, right? Because it has lower spillage, right, of energy. That's correct. And now how about massive MIMO?
This massive MIMO is suitable for small cells, that is femtocells.
Yes, but also you can use it at macro cells. And I'm saying if you have a macro cell with traditional MIMO or massive MIMO, I'm claiming you can serve more users with massive MIMO. Why is that? Am I right? What can you do better? Beamforming, right? You become very precise. Again, assuming you can do it, you solve the RF chains and everything, right? You can become very precise. So what does it mean? That if I have two users close by, with the traditional MIMO, I have to pick which one of the two to serve, because I can't serve both normally. Potentially with massive MIMO I could, because I could form two narrow beams and they would not interfere with each other. So that's kind of the idea. So now they are both about, I mean, not only about that, but they are both also about serving more users than we can do nowadays. So can we combine the two? We tried. So there is a bit of details on the model. I don't want to swamp you with math, but just to give you some idea. So the important thing is here that the interference and noise term is confined to being the imaginary part, this Q of L. So again, we combine things so that we can use linear processing. Okay, so I mean, I cited a paper in my slides where there are the details. So you can do match filter, you can do MMSE. Now, match filter is pretty much about multiplying. So if you look at it at the receiver side, you are multiplying the channel matrix with the emission of that, which is essentially conjugate transpose. It's not the inverse. The thing you should do, I mean, if you really want it to be correct, is like what zero forcing does. You multiply by the inverse, right? The problem with the inverse is like it's complex. Especially if you have a large matrix, to compute an inverse, it takes effort. So that's why match filter is okay, because you don't have to invert anything. Just take your matrix with a bit of scrambling and that's it, right? It's easy. What is the problem though? Is that if you multiply, let's take the real case. Forget about conjugate. Let's take just the real matrix, real numbers. If I do the transpose and I multiply by the matrix, unless you have a symmetric matrix, you don't get the identity. The only case where you get the perfect inversion is when for a special class of matrices which is called symmetric. Normally matrices are not like that though. So what you get is not the identity. You are not inverting the matrix, right? But you can show again, because of large number, law of large number and random matrix theory, that if you increase the number of antennas a lot, possibly to infinity, it will become like doing the inverse. With the advantage, it's much simpler. So you can show actually not for an infinite number of antennas, which is not practical, but for a large enough number of antennas, that the performance of match filter actually is not bad. Okay, it tends to be more and more like the case where you actually do the inverse. You can also do MMSE, which is essentially like doing the sorry? Yes, this is we are using CMT here. Yes.
The baseband representation.
Yes, yes. This baseband. Yes, this is like all digital signal processing. So this is all baseband processing. Yeah, we don't do any. There's no RF model here. Yeah. Okay, so MMSE is essentially like doing the inverse, like zero forcing, but you have to take into account the noise enhancement. I think most of the people will be familiar with this. Maybe some people are not from FIDO. Anybody that doesn't know about noise enhancement, MMSE versus zero forcing? You all know? Yes? Okay, good. So I don't have to explain that. So essentially you can do this correction, right, of the noise term. Okay, then again you can compute the signal as soon as I don't want to tire you with math. Yeah, so you can get your signal expression. So basically, once you get your signal expression at the receiver, you can see what is the useful signal, first part, what is the actual thing that comes from multi-user interference, and then the noise, which is the last part. So once you get this, it's easy to compute the signal to interference and noise ratio. What do? You just take your absolute value squared, right? So this is like something, once you have a MATLAB line of code, we'll do that. The difficult thing is to get here, right? Now it's easy. Now you just get the power and end of the story, right?
You are exploiting this term also for the computation of the signal, this interference term?
You are actually, that's something you don't want, okay? So when you do modulation and demodulation, you are excluding it, but it is there. So it's not part of the processing, but then you have to account it for the signal to interference ratio, right? Because something that you have to consider anyway. Yes, yes, this is a signer. Same with MMSE. No matter the complication of the expression, it's the same story. Signal, useful signal, interference signal, noise, right? So we can write SINRs, correct? Now, the assumption here is that you can actually, you are taking a situation where the impulse response is flat over a subcarrier band. That's not necessarily true, so we have to verify that. So we did some simulations and some analysis to check. What we found, again, I'm still not too sure about why, but it seems that if you combine filter bank and massive MIMO, you can use larger subcarrier bands than if you combine OFDM and massive MIMO. The reason still escapes me, honestly. Maybe this the leading PI will probably know better. I still don't think that's very intuitive. But what we saw, for example, is that you can have much larger spacing of subcarriers with FBMC, which has a lot of good implications if you have massive MIMO in terms of PAPR, because you have less subcarriers, CFO, channel frequency offset, because again, channel frequency offset is there at the boundary of subbands. If you have less subbands, you have less of this problem, right? So apparently that's true. Okay.
Slide number 94.
Yes.
In the last expression.
Yeah.
Look at the third term of the right hand side.
Yes.
There the I not equal to L is not mentioned.
Which one?
For the quadrature component.
This guy?
Yes.
Yes.
For
Yes.
the in-phase component, they have
Yeah.
mentioned the interferer from the intended one. They have separated by means of I not equal to L.
Mm-hmm.
For quadrature component, they have not mentioned I not equal to L, right?
Yeah, it's kind of complicated. So there is the math in the paper. So I don't think it's really too easy to do it right now. I mean, these are all defined in. If you go into the, I think we have a VTC paper in 2014. That everything is explained there. I think we could even share the thesis, which has the full story if you're interested. Okay. There is a guy that worked for 4 years on this, so we have a lot of details. And same with the GFDM. I'm just trying to give you an indication. Why am I putting some equations? Because I think it's kind of almost meaningless to talk about physical layer if you don't have any equation at all. So I still have to give you a sense of the math involved, but without digging too deep. Okay, so that I have to keep it at this level. But all of these things are kind of manipulations of the channel. So you take some combination of the real part, the imaginary part, you kind of vectorize them, so you do some kind of things. Okay. Okay. Anyway, you get your SINR. Now, because of the massive MIMO,
So can
yes.
you explain that 88 slide number
88.
CMT time frequency line.
Yes. So what?
What's the significance of this slide?
So basically, what you do, you have. So you always have a time and frequency plane, right? We say it in the beginning. So when you play with modulation, you have to consider both. So what happens in filter bank is that you give up the orthogonality between subcarriers, right? So that's still a problem. So you do it because you want to relax the synchronization, right? For some situation like massive IoT. The problem though still is not nice. So because you have this is intercarrier interference that brings down your signal to interference and noise ratio, right? It's a bad thing for the quality of the signal. So they are trying to put a patch. It's similar to what OFDM is doing with window wing for another reason. Here they are trying to upgrade the FBMC with things like toggling of the phase. So you are using orthogonal phases between adjacent subcarriers so that they kind of do not interfere with each other. That's what they do, okay? Because it's like a phase of 0 and a phase of pi over 2 are orthogonal.
So these are the phases of the adjacent carriers.
Yes, yes. So you basically, I think what they do, you do apply a different phase to the signal. So they are not. It's like if you think of it as a vector, one signal lies on the real axis, one lies on the imaginary axis. So if you take the scalar, the inner product is 0, right? They're orthogonal. So that's what they do. They do other things also, but that's one possibility. Okay. Yeah. Again, if you want more details, I think we can take it offline about the math. We do have. I think most of it is explained in the PhD thesis of this researcher. He finished the PhD in 2015. Still working actively on that. But the things I'm talking about are well explained in the thesis, so we could give you access to that if you're interested. Okay. Let's check time so we don't miss the picture. Any other question, comment? I suggest maybe one thing I can do, I'll try to get to the end. There's not much left, and then I'll open for questions if you have any. We are getting there, and it's not I have much more to say. So basically, the channel responses in the different receive antennas will be averaged out, no matter what combining you do, because of massive MIMO. So those of you that are familiar with MIMO diversity, they know what I'm talking about. Like, for example, techniques like Alamuti, they do what is called channel hardening, which is essentially averaging out fading. Yes? So you do some combining of the different signals so that you average out the fades. And you can do more and more of that if you have more antennas. Okay, so essentially massive MIMO turns pretty much anything you give to it into something that is just about long-term fading. Short-term fading is out of the picture. Okay, it's averaged out. So then it will only, it's kind of only dependent on, it will be only dependent on the distance and obstacles, path loss and shadowing. Fast fading is not something you retain with massive MIMO. Yeah. Now somebody could say this is bad because fast fading is what we use normally both in time and in frequency to do multi-user diversity, to schedule users. I have the hope, because the channel is varying in time and frequency, that if some user is fading in some position of the system, some other user is not. So if I have to pick between the two, I'll pick the one that is doing best at every time. That's what LTE scheduling is all about, for example. Okay. That's kind of gone with massive MIMO, but in a sense you care little because you have the degrees of freedom. You're moving them from time and frequency to space because of the array numbers. You can do better beamforming. So instead of dividing them over time and frequency, I'm dividing them over space now. So see, that's not such a big deal that you lose this fast fading, right, diversity. Another good thing is that because again of the degrees of freedom and these asymptotic laws that at some point start to kick in, you can get away with very simple techniques. You don't need like in the original version of spatial multiplexing, they had this BLAST technique from Bell Labs, right? VBLAST, DBLAST, and they use successive interference cancellation again, so non-linear, right, techniques, some complicated ones. Or you do have dirty paper coding, you have stuff like that. Maybe you have maximum likelihood, right? So you would need those if you want to achieve closer to the Shannon bound, or on the Shannon bound with dirty paper coding. You don't need to do that with massive MIMO. After the number of antennas is high enough, linear techniques will do. You'll get very close to the optimum. Okay, it's like what I was saying before, that if you multiply by, like, let's say match filter. It's a good example. If you have H, let's say transpose, if you have a real set of signals times H, for the number of antennas going to infinity, this is like H to the -1 H, right? It gets there. You start to have a diagonal, right? It's because of random matrix theory. There is quite a bit of work on that. Okay, so again, that's what we found. Open for debate. It seems that if you combine massive MIMO with filter bank, you have distinct advantages over combination of massive MIMO and OFDM. It seems that you can get away with larger subcarrier spacings, which has a set of advantages. For example, you have better deal in terms of carrier frequency offset, PAPR. Another thing is, like, this is due to the fact of having a better spatial confinement, so lower out-of-band emission. Of course, you can become more flexible when aggregating carriers, when doing spectrum sharing, spectrum coexistence, we know that. And you are more efficient bandwidth-wise for two reasons, because again, you are not wasting bandwidth waiting for the secondary lobes to become smaller, right? Like when you have a sync in OFDM. And another thing, it doesn't use cyclic prefix. So that's good for spectral efficiency, okay? Some results just to give a sense of what it is. So this is filter bank, multi-carrier, and massive MIMO. So we plotted here, we didn't consider the noise here. So we have only signal to interference ratio. On the left hand side, we have 32 subcarriers. On the right hand side, 64. Number N, capital N, it's the number of antennas at the base station. Okay. Users have one antenna only. Okay, so then you basically you see that increasing the number of antennas, well, you start to get better SIR, fine, but at some point that's not the point. At some point, the point is that it flattens. And again, that's the story we know with channel hardening from early space diversity works, but just brought to the extreme because you have 100 plus antennas. Okay. And this is with match filter. Now we're going to see how match filter does in comparison to something a bit better, MMSE. Okay, still single user case. We don't have multi-user here at the moment. So we are comparing here match filter with MMSE. Okay, so basically, okay, the more antennas you have, the better it is, clearly. So if I have 32 antennas, I will have lower. Here we are also adding noise. You will have lower SINR. If you have more antennas, you have better SINR, clearly. Okay, but the interesting thing here is that you don't lose anything apparently by doing MF instead of MMSE. Basically nothing apparently from our simulation. So why not using the simpler technique then, right? So because massive MIMO helps you with that. So that's one of the main advantages. I think you're kind of trading the complexity of the array, well, let's say of the RF and circuitry with the simplicity of the signal processing, so to speak. It's not going away. The problems are still there, but not on the signal processing side, so to speak. Another thing I want you to notice is that the user SNR is super small. Huh? The user SNR here, so this is uplink. The user SNR will transmit with -1 dB, which is fairly small. But basically the array at the receiver will boost the SINR by 10 log 10 number of antennas. So what does it mean? If you have 100 antennas, you boost the thing by 20 dB suddenly. It's a huge boost by the fact that you have such a powerful beamforming, basically, right? Same goes with downlink. I mean, okay, so that's a big advantage. So if you are about energy efficiency on the terminal side, massive MIMO is a good idea actually, because it kind of, you know, it relies a lot on the array gain you can get at the base station. All the works that we saw before on MIMO and multi-user MIMO, they normally assume more than one antenna at the mobile phone. This is not the case here. Okay. And then multi-user case, again, you start to see the problems that are there with match filter, right? Because you see, if you have a single user case, you don't have the problem, really much of the problem of the off-diagonal elements when you do the decoding, because that's where the interference would show up, right? It would be on the off-diagonal elements. When you do your processing, you multiply the transpose of h, again if you have real signals, times h, you would have something different than a diagonal generally, and the off-diagonal elements is where the multi-user interference shows, right? So it makes sense to me that you don't have problems with a single user, but you start to have them by this approximation with multi-user. You are not using the inverse here after all, right? Again, if you increase the number of antennas enough, you will start to see that things get better, but you probably need quite a few, okay, of them. Here we are seeing that with under 28 antennas, even you probably are better off with MMSE. So the asymptotic lows kick in later. So you still need something a bit more complicated than match filter, but it's still a linear technique. Okay, these are not complicated processing. So MMSE is fair. I'm just saying that, you know, there is a limitation to what you can achieve. Of course, if you're playing with asymptotic lows, you have to be in a regime that is large enough in terms of antennas. But still, it's an interesting result. 6 users are considered, and we have 2 cases of 64 and 32 antennas. Another thing I want you to notice is that if you use MMSE, you definitely have a flattened, a flat SINR, which is a sign of the fact that the channel doesn't change. You have averaged the channel, right? Which is why we can use larger spacing in subcarriers. So the processing of massive MIMO makes simpler the story about PAPR, carrier frequency offset. Anything to do with the fact that you have many subcarriers is simplified by massive MIMO processing. Okay, so you get better in terms of resistance to carrier frequency offset and PAPR. On top of it, you have the array gain, so the user really has a good deal here. Okay, possibly even you don't have to do this filtering done in LTE 4G, like this DFT spread, this single carrier FDMA, because already the massive MIMO is doing a lot of work, and filter bank is also doing a lot of work itself. Okay, yeah, so that's what I have about this. We still have a few minutes before the picture. I don't know if there is any probably time for a couple of questions or comments.
Yeah, I have a question.
Yes, please.
Actually, I can realize the graph has been plotted between normalized frequency and
Which slide?
these three graphs. Slide number 99, 98, 98, 99, 100. So
Yes.
these three slides.
Yes.
So actually, I can realize these graphs has been plotted between normalized frequency
Yes.
and
Yeah.
signal to interference noise ratio.
Yes.
With respect to different subcarriers like the 32 and 64 subcarriers.
Correct.
For n equal to 128 antennas at the receiver.
Yes.
So how many antennas placed at the antennas at the transmitter?
One.
Yeah.
Only one. Yeah. So you have in this case we have one user with one antenna, and then the multi-user plot is 6 users with one antenna each.
6 users, only one antenna.
One antenna each always.
So
Yes.
if I add more number of users, another 6 users, then I have to place one more antenna.
I think what would happen, you could still get away with one antenna. What I suspect would happen is that you would have a bigger discrepancy between match filter and MMSC because you have more multi-user interference. So the more you do that, the more MMSC will be better than match filter, right? Because match filter essentially simplifies the decoding because it doesn't use it uses the Hermitian, right, of the channel. It doesn't use the inverse. So the more you add users, the more you are getting away from a situation where the Hermitian approximates the inverse. Yes. So if I think the best way to see it is like when you multiply the Hermitian times the channel or the inverse times the channel. So single user and a lot of antennas, good. If you start to decrease antennas or increase users, bad. Then definitely the Hermitian is going to be different than the inverse. Yes? Any other question? Must be tired after, I think it was a bit of a heavy day today with physical layer, honestly, is a bit like that. Okay. So, but I think it's still a very good, even if you do, let's say, Mac or networking work, which is fine. I'm doing probably more Mac work myself nowadays. I think to have a good grasp of digital signal processing and, you know, like a file layer is never bad. I think this is something that, in my opinion, is something you should acquire or at least have some interest in knowing more. You see, in my experience, it's way easier to go from Phi to Mac than the other way around. It's heavily mathematical, so it's not a waste of time. Okay, so if you have some time to look at least into the basics of it and to be aware of the trends, you can use them better. You don't need to be very fluent in Phi. You need to know though what you can use. So if you have to design a system, you have to be aware of the options you are given by physical layer. That's important. Okay, so you can't really do a very good job in resource allocation if you don't really know what the resources look like, right? The resources are of a physical layer nature essentially. Yeah.
Sir, one question. In the case of SIC, suppose I have 2 users. So
Yeah.
first of all, the weakest user will decode his own signal.
Yeah.
The weakest user is
Not
decode his own signal, and
Hmm.
afterwards the strong user will subtract the
Is that always true? Isn't it also the other way around?
yes, it can be other way.
Because I think in SIC they normally do that. You pick the strongest one, right?
Okay.
Yeah, you subtract and then yeah,
Yes, yes.
because that's the one interfering the most system-wise. Yeah.
So
Yes.
Because we have to decode one after another.
Correct.
So how this decoding delay can be handled, or how the propagation error,
Yeah.
suppose it exists, then how it can be handled?
Yeah, so I think, I mean, there are works, especially in GFDM, with successive interference cancellation. They tend to be out of the game with massive MIMO because massive MIMO doesn't necessarily need that because of the high degrees of freedom at the base station. You normally get away with linear techniques. You don't need to do, it seems, I mean, that people are happy enough with zero forcing, MMSE, match filter. So if you have a large enough array, you probably don't need it. Now, if you have a low enough, if you do not have these numbers of antennas, then you might have to do signal interference cancellation, especially if you use these non-orthogonal waveforms. In that case, well, you have to compromise, I suppose, right? Because you have, essentially you're right. You have to wait more time.
If the number of users will increase,
Yeah.
the decoding delay will be increasing
So
proportionally.
true, yes, and I think you might have. Well, I know people. I'm not really into that field, but I know people have been doing also what they call PIC, parallel interference cancellation. Might be faster. I guess you could still find simplification. So as we did for linear techniques, where we brought down the computational complexity by playing with tricks of linear algebra, you find regularities right in the structure of the matrix, and so you don't need to compute everything. You just compute a bit of it. Maybe you could do similar things in SIC. Things are though more complicated because there is entanglement between the different stages. You have error propagation. These are not there in linear techniques. Linear techniques are one shot, right? Non-linear starts to be more complicated. But yeah, I think that's a relevant question. I think if you cannot afford for too many antennas and you have non-orthogonal waveforms, then maybe you have to give up mobility. Yeah, possibly. Yeah. Maybe a last question, and then we go to take a picture altogether in the sun. Go. Okay. Picture time. Yes. Good. Yeah. So I won't be here for the exam today. There will be somebody.